Hello, chemistry students. So I didn't want anybody to be deprived of this opportunity to learn about the gas laws. I did this on Monday with my A-Day group, and I've since been quarantined. So I figured I could do this video and just kind of go over, put basically the entire gas laws unit on a single whiteboard, and had all the information there in one place. So I thought that I could share this with you, and maybe it would help you. So that's what I'm going to do now. So gases are the least dense state of matter. The particles, the molecules, or the atoms are the farthest apart in gases. And something that's neat about gases is that they do expand and contract predictably, which means you can model them with equations. Different scientists model different features of gases. So Boyle's law says that if you decrease the volume of a gas, in other words, if you squeeze the gas together, the pressure increases. You probably know this from maybe squeezing a balloon or something like that. The harder you squeeze, or the more you squeeze the balloon together, the harder the balloon pushes back on you, indicating more pressure. So the mathematical relationship from Boyle's law is that the initial pressure times the initial volume of the gas equals the final pressure times the final volume of the gas. And we use ones and twos to indicate initial for one and final for two. Now, when you solve problems, you can use this equation, but you have to use it just keeping in mind that you're going to use your reading comprehension skills to figure out which is the initial and final pressure and volume. Now, the units of pressure 1 and pressure 2 must match each other. Like, you couldn't combine atmospheres and PSI, like that wouldn't work. And the same thing with the volumes. The units on the volumes have to match. So like, if you get a problem that has milliliters for one volume and liters for the other volume, then you would need to convert one of the units so it matches the other one. All right, Charles' law says that if you increase the temperature of a gas, it expands. And this has a specific application to hot air balloons, because that's how they make the hot air balloon buoyant, is they heat the gases inside of it up so that the gases inside have a lower density because they've expanded than the gases outside. So the hot air balloon, therefore is less dense than air, so it'll float. The relationship mathematically is volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. The units for volume and temperature must match, and temperature 1 and temperature 2 must be in Kelvin in order for this equation to work properly, because this proportionality is only true for when the temperature is based on the absolute temperature starting from 0 Kelvin, which is absolute 0. So convert your Celsius temperatures to kelvins before using Charles' law or Gay-Lussac's law or the combined gas law or the ideal gas law, which we haven't gotten to yet, but I will get there in a second. And it's easy to convert from Celsius to Kelvin. If you have the temperature in Celsius, add 273 to get the Kelvin temperature. If you have the Kelvin temperature and you want to get back to Celsius, subtract 273. Now, Gay-Lussac's law says that if you increase the temperature, the pressure increases. Okay, and that's why things are more likely to pop or blow up when they get hot than when they're cold, because as you increase temperature, pressure rises. Basically, it makes the molecules move faster and push outward more. Now, the pressure units have to match one another in this equation, and the temperatures must be in Kelvin. So that's something with gas laws. The temperature always needs to be converted into Kelvin. Now, all three of those relationships can be put together to get the combined gas law, which has P1V1 over T1 equals P2V2 over T2. And that's yeah, I guess you could see it's kind of like all these equations put together, because you see the T's are always on the bottom and the P and the V are always on top. So you can put all these together. So you could have as many as 3 variables changing at a given time, and that would give you the ability, if you have all 5, you can solve for the one that you don't know. Now, when you solve for a variable, I recommend that you go ahead and do this algebraically first. And a good first step is to cross multiply, so you get these t's out of the denominator. That leads to a lot of algebra errors when people leave those t's down in the denominator. So when you cross multiply this out, you get p1 v1 times t2. That's where this comes from. And p2 v2 times t1. And I gave the example like, hey, if I wanted to solve for t2, then what do I need to do? Well, I need to isolate t2, so I would divide both sides by p1 v1. So this p1 v1 cancels out, and that means that practically to solve for t2, I would multiply pressure 2 times volume 2 times temperature 2 divided by pressure 1 and times volume 1. Okay, that's a lot of stuff, and that's why I do this way, because you'd have a lot of numbers here to do algebra with, and I prefer to do algebra with the symbols than the numbers, especially when there's a lot of symbols. So some of you may feel more comfortable doing it with the numbers, and that's fine, but you're probably more likely to make a mistake if you got a lot of numbers floating around. Now, when do you use the combined gas law versus the ideal gas law? So I talked about this yesterday with my A group. The combined gas law, there's going to be some kind of change in pressure, volume, or temperature that signals that you need to use the combined gas law. And sometimes one of the variables will stay constant. They either don't tell you about it or they tell you it stays constant. Either way, that means that, like, say for example, if the temperature stayed constant during a change of pressure and volume, then if the temperature is the same number here and here, it cancels out. So that would leave you with just Boyle's law. So Boyle's law applies to the combined gas law, or Boyle's law is the combined gas law when temperature is constant. Charles' law is when the pressure is constant. You see, cancel out pressure, you get V1 over T1 equals V2 over T2. And then Gay-Lussac's law would apply when the volume is constant. Okay, when do you use the ideal gas law? Well, anytime that there's not a change in temperature, pressure, or volume, and they'll have something in there about moles or grams, and you might solve for the moles, or you might solve for something else knowing the number of grams or the moles. Let me talk about units of pressure for just a moment. So on the surface of the Earth, on average, at sea level, the atmospheric pressure is 1 atmosphere. Somebody smart came up with that. Other units that same pressure can be measured in. PSI is 14.7. In millimeters of mercury, it's 760. Torrs is also the same, at 760 millimeters of mercury. And then also there's kilopascals, or kPa, so that's 101.325. All those quantities are equal. So let's say that you had atmospheres and you needed to convert to millimeters of mercury. Well, you could do that because you could take the atmospheres and then do dimensional analysis, train tracks. 1 atmosphere on the bottom is equal to 760 millimeters of mercury. And then your atmospheres would cancel out because you have 1 in the numerator and 1 in the denominator. And that would convert this 325 or 3.25 atmospheres to millimeters of mercury, whatever that is when you multiply 3.25 times 760 and then divide by 1. You could also convert to kPAs. Remember, the kPA is 101.325. It's equal to 1 atmosphere. So set it up in a similar way. The atmosphere is on the bottom and the kPa is on the top, and you would multiply and divide by 1, and you'd be able to get the kPa's there. All right, let's talk about the ideal gas law a little bit. So the ideal gas law relates the pressure, volume, and temperature of a gas to the number of moles of the gas. And there is a gas constant in there to make all the units convert so that you actually get moles. So the gas constant is on page 1 of your reference table. All right, here you go. So here's the gas constant. There's 3 different versions of it. So there's the liters times atmospheres over mole Kelvin version, which is 0.0821. There's the liters times the millimeters of mercury over moles Kelvin version that's 62.4. This also works for torr because remember, 760 millimeters of mercury and 760 torr are identical. Millimeters of mercury is named torr in honor of Torricelli for his work identifying atmospheric pressure and how it's related to weather, which is a neat story. I would recommend you look it up. Anyways, and then there's the liters kPa over mole Kelvin version of the gas constant as well. And the way you pick which gas constant to use is you just choose the one that matches the unit of pressure. So the gas constant must match the unit of pressure on page 1, and it's on the page 1 of the reference table. So like, let's say your pressure was in atmospheres, then you would use this one, 0.0821, as your value for R in the gas constant. Let's see, pressure, volume. The volume has to be in liters because remember, the gas constants all have liters in them. So if your gas volume is not in liters, then the units will not cancel out properly. And the temperature has to be in Kelvin. Also, the gas constant tells you that. So the units have to be consistent there. Now, I wanted to point out here with the number of moles, okay, once you get moles here, you can take that into a mole map and go anywhere you want to, like particles or grams or whatever, or even into stoichiometry for that matter, which AP chemistry students struggle with that sometimes. But remember, you can use the molar mass to convert moles to grams or from grams back to moles. So sometimes the problem will ask you to solve for grams. That means you need to solve for moles and then convert it to grams with the molar mass. Or sometimes the problem will give you grams and then you have to convert the grams to moles and then plug it into the equation to solve for one of the other variables. Also, another point that I'll make here is if you know, say, from the ideal gas law, the number of moles of a gas, and you also are given the number of grams of gas, you can find the molar mass of the gas and identify it by doing grams divided by moles for the gas. Or you can find the density of a gas if, say, you know the mass of it, and maybe you could find the volume from the ideal gas law. Then you could do mass divided by volume to find the density of the gas. So there's a lot of possibilities here with the problems. How you can use these. The ideal gas law is a very, very useful relationship. Now, I gave an example over here. Oh, one more thing. So standard temperature and pressure is referred to sometimes. And that standard temperature is 0 degrees Celsius or 273 Kelvin because that's the temperature of an ice-water mixture. So it's very easy to create in a lab setting. And then standard pressure is just 1 atmosphere. And remember, there's a lot of different units that 1 atmosphere can be expressed in, whether it's 1 atmosphere, 760 millimeters of mercury, or 101.325 kPas. If you ever forget what that is, it's also on page 1 of your reference table. See, here's standard temperature, 0 degrees Celsius or 273 K. And here's standard pressure, 1 atmosphere equals 101.3 kPas equals 760 millimeters of mercury equals 760 torr. Now, I gave an example of what you would do to solve for volume here. This is not the same step you would follow every time you're going to be doing algebra with both of these equations, whether it's combined gas law or ideal gas law. So I gave the example, if you wanted to solve for volume, then you would divide both sides by pressure. So you get volume equals nRT, moles, gas constant, temperature over pressure. And I did an example where we were at standard pressure and standard temperature, and we had 1 mole of gas, and divided all that out, and you get 22.4. And it's like, hey, that's the molar volume. And remember, we got that back in the mole unit for the volume of 1 mole of a gas at standard temperature and pressure. Thanks for watching. Hope it helps.